In question 7, we're given a 2 by 2 matrix A, the matrix 1, 3, 2, 1, and we're told to factor it as a product of elementary matrices, which is something we can always do to any matrix as long as it's an invertible matrix, which this must be by implication. And basically what we need to do is we need to figure out what the steps would be to take this matrix A and bring it to reduced row echelon form, which would have to be the 2 by 2 identity matrix. So we don't need to augment this matrix or anything like that, because we're not actually looking to compute the inverse in this case. I simply take the matrix 1, 3, 2, 1, and I bring it to its reduced row echelon form. In the first column, the pivot is already a 1, so I don't need to worry about that. I just need to get a 0 below that pivot. So I'm going to subtract 2 times row 1 from row 2. So the first row stays 1, 3. The second row becomes 2 minus 2 is 0. And 1 minus 6, which is negative 5. Now, in reduced row echelon form, my pivots must be 1s. I discussed that fairly extensively in the video for question 6, in case you haven't watched that yet. So we need to take that pivot in the second column, which is currently a negative 5. We need to turn it into a 1 by dividing by negative 5 or multiplying by negative 1/5. So again, the first row stays the same, and the second row becomes 0 and 1. And then finally, because this is reduced row echelon form that we're looking for, we need to turn the entry above that pivot, which is currently a 3, into a 0. So our last step of Gaussian elimination is to take row 1 and subtract 3 times row 2. And that gives us, as expected, the identity matrix, the matrix 1, 0, 0, 1. Now what we want to do is we want to figure out what elementary matrices correspond to each of those steps of Gaussian elimination. So first of all, we took row 2 and we subtracted 2 times row 1. So the corresponding elementary matrix can be found by taking the 2 by 2 identity matrix and subtracting twice its first row from its second row. So if I call that E1, well, of course the 2 by 2 identity matrix is the matrix 1, 0, 0, 1. So if I subtract twice the first row from the second row, I get the matrix 1, 0, negative 2, 1. The next step of row reduction that I did was to take row 2 and multiply it by negative 1/5. So again, to get the corresponding elementary matrix, I take the 2 by 2 identity matrix and I multiply its second row by negative 1/5. So that would give me 1, 0, 0, negative 1/5. And finally, the last thing I did was I subtracted 3 times the second row from the first row. So again, I come back to the 2 by 2 identity matrix, subtract 3 times its second row from its first row, and so that will give me 1, negative 3, 0, 1. But what I've got to be careful about here is that those aren't the elementary matrices that I'm looking for to be the factors of my matrix A. Because what this actually means is that if I start off with the matrix A and I left multiply it by E1, get a new matrix. And then I left multiply that by E2 and get a new matrix. And then left multiply that by E3, the result of that process will be the identity matrix. So E3 times E2 times E1 times A gives me the 2 by 2 identity matrix I. Which in turn tells me that because elementary matrices have to be invertible, if I take each of these matrices now and go through and multiply by the inverses, I can do that on each side. That will tell me that A is equal to E1 inverse times E2 inverse times E3 inverse times the identity matrix, which I can leave off now because, of course, anything multiplied by the identity matrix is itself. There's my factored form. But that means I need to figure out, based on these three elementary matrices, what their inverses are. And there's an easy way to do this and a hard way to do this. The hard way to do this is to say, well, these are all 2 by 2 matrices. We've got a process for computing the inverse of a 2 by 2 matrix. And we could go through that. But we don't need to. Because it's actually very easy to figure out the inverse of an elementary matrix. All we do is we reverse the row operation that led to that elementary matrix, and the elementary matrix that corresponds to that reverse process is its own inverse. So for example, the elementary matrix E1, we obtained that by subtracting twice row 1 from row 2. We would undo that by adding twice row 1 to row 2, which means that E inverse, or E1 inverse I should say, is obtained by taking the 2 by 2 identity matrix and adding twice its first row to its second row to get the matrix 1, 0, positive 2, 1. Likewise, the second step we did was we took row 2 and we multiplied it by negative a fifth. That's what the elementary matrix E2 represents. We could undo that by taking the second row and multiplying by negative 5. So again, take the 2 by 2 identity matrix, multiply its second row by negative 5, and we get the matrix 1, 0, 0, negative 5. And E3 inverse, well, we got E3 by subtracting 3 times the second row from the first row. We undo that by adding 3 times the second row to the first row. And if we do that to the 2 by 2 identity matrix, we get the matrix 1, 3, 0, 1. So the factored form of A, then, is to write it as the product of the matrix 1, 0, 2, 1 times the matrix 1, 0, 0, negative 5 times the matrix 1, 3, 0, 1. That's how to get A as factored as a product of elementary matrices.